Okay, let's continue our discussion on high frequency and whether we can ignore it or whether we have to include it in our system. And we looked last time and we found that if our dominant poles are 10 times less than our high frequency, then we can ignore the high frequency in our system. Or said another way, if our high frequency are 10 times greater than our dominant poles, we can ignore the high frequency. So that's going to be our rule of thumb, our criteria. Let's see how we might implement that and decide whether they're high frequency or not. The type of problem that you can run into on this is like the problem on our homework. If we have a transfer function, in this case I'm just going to, and this is a closed loop transfer function that I'm giving you now. Let's just imagine a closed loop function, let's say 50 s plus 1, I'm sorry, s plus 5, s plus 50. Okay, just a simple second order system. And can we ignore the high frequency on this? And if we look at this is a closed loop system. We know that we've got a pole here at 5 and we've got a pole here at 50. There's a 10 times relationship in there. So we could just ignore this pole at 50 and expect to get very similar results as if we include it, because it's happening so fast that it really does not affect the output of the system. So how do we ignore that one? Well, we're going to write an equivalent where we just ignore it. And so we're going to have a 50s plus, 50s s plus 5. Okay? Now, the problem, if we stop at this point, we get a mismatched KDC. The systems are not equivalent. The KDC for our system with a high frequency is different than the KDC for a system where we've ignored it. We want to have the same KDC. So what we're going to do is going to put a variable in here in x and use that to match up our KDC. So if we come over to our high frequency and calculate our KDC, or our DC gain, as we've called it also, remember to do this, we just set our S is equal to 0, and so we end up with 50 over 5 times 50. And that would be our KDC. In this case, it's pretty easy. It comes out to be 1/5 as our KDC. Okay. Now, what we want to do is have our KDC for our new system to be equal to 1/5 also. And so we do the same. We calculate the KDC on this, set our S is equal to 0, and we end up with 50x over 5. Right? And so we do a little bit of math on this, and we end up, we can do it a couple ways. I'm going to cancel this out, make that a 10. So 1/5 is equal to 10x, which means that x has to equal 1 over 50. So our final reduced order model, is going to be 50 times 1 over 50 divided by s plus 5, or simplifying that, 1 over s plus 5. Okay, so this would be equivalent to this. They would be equal because they had the same KDC value, and our high frequency stuff is ignored. High frequency being frequencies or poles larger than our dominant poles or our slow poles close to the origin. And so that would be how you would go about working the problems on the homework. They're really pretty easy. Now remember, we're talking about closed loop poles here, closed loop poles. And so you want to make sure that you have that. Now, another way that we could look at this that I like to include on some tests is, what if we have a system like this? look at the open loop system. And in this case, let's use a G, and let's put 1 over S plus 2 and S plus 40. 40 in there. Okay, that's a 40. Like this, and close that loop in there, and look at this system. Let me clean that up because that looks really horrible. All right, so we look at this, and our first inclination might be to say, oh, well, 40 is much larger than 2, so I'm going to ignore the 40. And if you do that, then you would be in error, because we can't make that assessment in our open loop. We have to make the assessment in the closed loop. Okay, and the closed loop poles depend on the value of K. Okay, depends on what our K does in here as to where the closed loop poles are going to go. Okay, I've set this problem up in MATLAB, and so let me pull up MATLAB, and here I've got our MATLAB script, and I've defined a G in here with the same characteristics. And now I'm going to take this into SisoTool, and SisoTool will do the feedback of my transfer function, my open loop transfer function, and then allow me to vary the gain on that and see what happens. And so if I look at my SisoTool, you can see the root locus for this, and it's as we expect. It's just a simple second order system that we have poles, open loop poles at -2 and -40, and we get a response, and sure enough, it's dominated by this pole here at -2, and we can see a half 0.5 time constant, which is what we would expect. It's pretty first order-ish. And so if we had the gains low, and we see the gain over here at 0.007, if we had the gains really low, we could go ahead and eliminate that pole at 40 and just make a simple first order system 1 over S plus 2. Now, let's look and see what happens when we start up in the gain. Okay, up in the gain. Remember, these pink dots are our closed loop poles moving along on our root locus as we increase the gain here. So I increase the gain, and now what happens? I've got a pole here at roughly -5, and I've got a pole here at 37. Don't have the 10 times rule in here, and we can start to see that here in our system. We're starting to get it distorted from a true first order system. We're starting to pick up some interaction between of this faster pole out here is starting to reshape our first order associated with our slower pole. And so in this case, we could not eliminate that 40 because our closed loop poles resulting from the gain of 86 does not allow us to maintain that 10 times rule. And of course, we could go ahead and increase the gain even more, and we see a more dramatic effect on here, and we definitely could not eliminate this because now we've got it about our dominant or our slow pole is at -12 and our faster pole is -30. There's about a 2 times relationship in there, so we couldn't eliminate. And of course, we move it even closer. We can't, and we can't either when we move it off axis either because they're equal in frequency as complex poles. And so going back to our system in here, if I ask you to create an equivalent, or could you create a reduced order model for this system, you would come back and say, what is K? Because you have to know K before you can determine whether the poles are in a location, the closed loop poles are in a location, so that you can determine whether you have the 10 times rule in the closed loop so that you know whether you can eliminate the open loop or not. Now, if you want to get really interesting about this, you could come in here and solve this closed loop for k, and then solve for the 10 times rule on that, and determine what your maximum value of k is that you can have, and still eliminate your high frequency pole at minus 40. So anyway, that's where we go with this. But typically what I will do is I will give you a k value. I'll say, oh, k is equal to 10. And then say, can you write a reduced order model for this system? And knowing that k is equal to 10, you would do your block diagram algebra and come out with a closed loop transfer function and determine whether your closed loop poles can be eliminated or not, and then proceed from there as to writing a reduced order model. But remember, the reduced order model, you need to have the same KDC. So if you do the reduced order and decide to eliminate it, be sure and match a gain with that for your transfer function to be the same KDC. Okay, so that's about all there is with high frequency. So we should be done with that, and I'm going to move on to the next topic.